Mr. E. Harikrishna, sir, currently assistant professor in Kakatiya University, Kottagudem, and sir is doing his PhD in the area of signal processing for communications under the guidance of our coordinator and principal of this college, Professor K. Ashok Reddy, sir. And E. Harikrishna, sir, has published nearly more than 70 articles in various journals, reputed journals and conferences. And sir is also a reviewer for various reputed journals. And sir also acting as a coordinator and a resource person for various programs, in and around this city. Thank you, sir. Thank you very much for accepting our invitation. Please, you can start your presentation, sir. Thank you.
Sir, thank you very much. For me to take the opportunity to deliver some of the insights of signal processing methods for OFDM channel estimation. Thank you for introducing, sir. Thank you very much. The coordinator, sir, principal, management, and department of ECE for giving me this opportunity to deliver a lecture on OFDM channel estimation methods. So I will directly go to the presentation. So, sir, the presentation is visible, sir?
Yes, sir, it is visible.
Yeah, okay, done. So, good afternoon to you all. Want to deliver the channel estimation methods for OFDM systems using MATLAB. So, a form of communication, there has been a major changes from the last couple of years, but it's always a challenging job to estimate the wireless environment. But we can simply say that we are estimating the either channel impulse response, emissions, noise variance, and some other parameters are there. We'll discuss those. So, estimation of those parameters will influence the received signal. So, in general, for a digital communication system, the comparative measure is bit error rate. Comparative measure will be bit error rate. So, signal processing methods to improve the channel estimation so as to improve the quality of the received signal, nothing but improving the bit error rate. So, of bit error rate is preferable. In general, I will say 10 power minus 12 is my preferable value. I can say it's ideal value. The value of 10 power minus 12. But in general, in almost all papers, rate or symbol error rate will be in the order from 10 power minus 4 to nearly some 10 power minus 7 or 10 power minus 8. So specifically concentrating on the OFDM systems. It is used in 4G communication systems and even in 5G communication systems. It will be the part, not in a straight way, with some modified versions. Either I think it will be used either in downlink or uplink cases. It will be useful. Some disadvantages are there but still it is providing a good solution to 5G communication system also. So this is a complete OFDM transceiver system, forward error correction coding, error detection and correction, bit interleaver. It will convert burst errors, group of continuous errors that will be distributed into a different frames. So bit interleaver converts burst errors into single bit errors in a frame. Different interesting issue actually, bit interleaver. Then as usual, the modulation, either QAM or PSK, serial to parallel conversion. This is the diagram I think you have seen in yesterday's class, mostly with MATLAB also. The point of interest here is the channel estimation part. Channel estimation part. So this is actually the diagram copied from this book, Wireless Communication System with MATLAB. Good number of MATLAB programs are available in this book. You can refer this book. So similar to this block diagram, same is represented in the form of a mathematical equation. So first DFT will be performed, guard interval, then channel. So it is a circular convolution with additive white Gaussian noise, DFT operation, then estimation of channel. See, in general, we can say that this wireless environment is completely a system. But we cannot say it's a simple LTI system. What we'll generally read in our books, linear time invariant systems. Mostly in our books, we'll concentrate on LTI system, linear time invariant system. This wireless environment, this wireless channel is a non-linear, time-varying, random. The prediction of that is a very tough task. Maximum satisfaction level, improved output signal rate can be the good quality. We cannot achieve ideal value, but a good quality of received signal is preferable. So we'll see that. Navigation to show what is the need for channel estimation. The transmitted signal will be modified in the wireless channel and it is received at the receiver. So X, H. So this is a completely a wireless channel with impulse response capital H. So Y is equal to H impulse response convolution with X. Feed the transmitted signal back. So Y deconvolution by H. That is Y deconvolution H. So how do you get this H is important one. How do you estimate? Estimate of H can be done is an important task. So wireless channel, similar discussion just now I mentioned. It can be seen as a non-linear time varying system. It can be seen as a non-linear time varying system and a random impulse response. It's a random in nature. So there exists some physical phenomena in the environment. That is the existence of line of sight, reflection, refraction, and diffraction. Using mobile phone, they are moving. So either source of oscillation or observer of oscillation is in apparent motion, or in motion, see shift takes place. So if I transmit F0 signal, relative velocity of the mobile, Doppler shift will comes into picture. The received signal will maybe F0 plus or minus Fd. When you are approaching, it is increasing. When you are moving away, it is decreasing. So F0 plus or minus Fd. The received signal will be that Doppler shift. So these are all phenomena, natural phenomena that occurs in the environment, because of which degradation of signal quality will take place. Of large background noise, the best signal, it's always a tough and challenging job for a communication engineer. Receiver with eliminating completely the noise is always a challenging job. So these physical phenomena are there. We'll try to get the point from these physical phenomena. Travels through the medium noise. It is difficult to model the real world environment. Exact modeling will not be done. In some constraints, based on the scenarios and examples, we'll consider different models. Each model will have its own advantages and disadvantages. So this is the received signal, that is with reference to distance, how the signal is varying, the received power, transmitted power, we can say it's attenuation, path loss, fading. If you receive multi-path component, the received signal will be the vector addition of multi-path components. Sometimes, if the two received components are, then the resulting signal will be 0. That is one signal received with X, another received signal with X at the rate 180 degrees with a different phase, so which is minus X, and output will be 0. So sometimes the signal may increase, sometimes signal may decrease. Mechanism, multi-path components, fading phenomenon comes into picture. Fading is a long-term fading, slow fading, and fast fading is there. This is how you can see multi-path fading component scenario. Different components, same copies will be received after with the different phases. So this is a classification. Fading channel. Large scale fading, small scale fading, path loss, shadowing, multi-path fading is divided again into two parts: frequency selective fading and flat fading. Means all frequency components will be faded by same way. Frequency selective fading is some particular frequency components will fade in different way. Slow fading is because of Doppler shift. So all these physical phenomena and classification, we will develop a model. Already established models are there. Based on the application, based on the scenarios, we will select one of the channel. We'll select the channel model. So what we have to understand, or we have to consider the parameters. Carrier frequency, say consider 2.4 gigahertz or 5 gigahertz, say some 20 megahertz or 40 megahertz. Delay spread, Doppler spread, mobile speed. So the strategy is start with some physical models and end with the statistical models. Start with some physical models and end with some statistical models. Some assumptions. Without that assumptions, we will not move further. We cannot design an ideal wireless channel, ideal wireless model with considering good number of constraints. We will design channel model. So channel modeling is important. Number of established channel models are there. See channel models. free space propagation model, old one model, empirical model, ERSEG model, relay. All these will consider either relay feeding channel or Russian feeding channel, different channel feeding mechanisms. These mechanisms can be found in MATLAB with a function, with a predefined function. If you give for that function input as a transmitted signal, output of the wireless environment, good number of channels. You can use those functions. So we'll see with an example how we can use the channel models. So I'm considering a simple affair filtering model. Channel impulse response. Be a delta of n minus k, delayed impulse. Delta of t minus 1, delta of t minus 2. Sorry, n, because it is a discrete time system. We'll consider delta of n minus 1, n minus 2, and so on. Of n is the attenuation incurred during that path. Attenuation incurred during that path. So a simple example I'm showing here. You can generate in the MATLAB where is a random integer values as an impulse response. As you can generate a complex impulse response also using MATLAB. We'll see that examples. Feeding channel, Russian feeding channel. These are all feeding channels for these functions are available. The inbuilt functions available in the MATLAB. But try to understand those feeding channels, characteristics of those feeding channels, get the output perfectly. So, Rayleigh feeding channel response is modeled as zero mean complex valued Gaussian process. Complex valued x plus jy, both are Gaussian. Feeding channel is a Rayleigh, x plus jy, x is a Gaussian random process, y is a random process, and it's a Gaussian, and it is a complex valued Gaussian random process. As a zero mean, that is a Rayleigh feeding channel. We can directly generate the functions, no problem. So, Russian feeding channel is, except it consists of a strong dominant LOS component, line of sight component, will be the difference. So, depending on the application, you have to use these feeding models. I will take off one work. I will simulate with all feeding channels and I will test my signal processing method. That's also better. All feeding environments. But your method may resulted in good performance in some environments and may not good in all environments. You can conclude that in your article. So it's better to test our proposed signal processing method or any other any other methods can test under different feeding channels to test the performance of the proposed method. So based on some literature available in the, I have classified the channel estimation into some parts: blind, non-blind, semi-blind, sparse. So non-blind can be divided as a data aided and non-data aided. Adaptive, block type, comb type, lattice type. These are all pilot channel estimations. Pilots means known symbols transmitted to the receiver. Not continuously, yet with some difference between the samples. We'll see that examples We'll see that examples. Precision directed channel estimation, discrete Fourier transform based channel estimation, expectation maximization or maximum likelihood, least square estimator, minimum mean square error estimator, and interpolation. I will consider this part. Data aided channel estimation method. Non-blind channel estimation, data aided. These are all the methods. Blind channel estimation means it doesn't know any information related to channel. No channel state information is provided. Using some statistical models, it will model the environment, wireless channel. Semi-blind, it's not completely blind, not completely non-blind. Using the advantages of both blind and non-blind, a blended mixing, blind channel estimation. Then sparse channel estimation. In some cases, sparse channel sparsity estimation of the impulse response. Certain cases, impulse response is 0. So estimation of that 0th sample of the is important. That is a sparse channel estimation. This is only some basic channel estimation methods are considered. Good number of other methods also there. Concentrating today's class, estimation using this data aided non-blind channel estimation methods. Specifically, least square estimation, minimum mean square error estimation with using all these three: block type, comb type, lattice type, and interpolation. We'll see that. Block type pilot arrangement. In a time domain, you see, this is one ofdm symbol. I am providing pilot at this place, pilot with unknown symbols in the middle. The separation between these two pilots is ST. This is block type pilot arrangement. Known symbols, known information. Pilots are known symbols transmitted by the system. Receiver. So we can estimate the channel at this instance of time, at this instance of time, at this instance of time. And once the channel is estimated based on the pilots, based on the known pilots, using interpolation mechanisms, using step interpolation, different interpolation mechanisms, will estimate the channel. So this block type pilot arrangement is suitable for frequency selective fading channel. It's suitable for frequency selective fading channel. This is home type frequency, home type pilot arrangement. It's a home type pilot arrangement. So one complete symbol is a pilot. You can see that space between the two pilot symbols is in frequency domain. That is SF, which is suitable for a frequency fast fading channel, and it is a frequency interpolation. I will estimate at this place channel, I will estimate the channel at this place, and I will estimate at this place. Then I will do some frequency interpolation mechanism to estimate the final channel. So these are all pilots, known symbols arrangement in a ofdm symbol. So this is the combination of both time and frequency, both block type and comb type, suitable for both the time varying and frequency varying fast fading channels, where here you can do both the time interpolation and frequency interpolation mechanism. Pilots spacing. Pilots are known symbols. So we'll see some good amount of mathematics here. So from the block diagram, after QA mapping and serial to parallel conversion with addition of CP, this is simply DFT formula. X of k is equal to sigma k is equal to 0 to n minus 1 x of L. Then addition of CP, cyclic prefix is added. You know, all, I think, importance of cyclic prefix. Then this is a channel impulse response. Output is y is equal to h circular convolution x plus v, additive white Gaussian noise channel. Additive white Gaussian noise. So that is the output. Y is equal to h convolution x. So I'm doing some applying DFT. So circular convolution in time domain will be the multiplication in frequency domain or a DFT domain. So y of L is equal to h of L into x of L plus z of L. V of L, I am assuming it as a z of L. Now substituting values from 0 to n minus 1. Y of 0 is equal to x of 0, h of 0 plus z of 0. Continued up to y of n minus 1. So I want to represent this in terms of a matrix. So that's why I have substituted all the values of L from 0 to n minus 1. Now I will represent it in the form of matrix. Received output signal in frequency domain. This is transmitted signal in frequency domain. This is impulse response in frequency domain. This is noise in frequency domain. So I will represent this as a matrix. Y bar is equal to x h ofdm symbol output in matrix form. Simple explanation. A beautiful thing can be understood from that is, it consists of the transmitted signal matrix. It consists of only all diagonal elements are the signal elements and all remaining are zeros. Because its inter-channel interference and orthogonality is maintained, the other values are zeros and x of 0 to x of n minus 1. It consists of only diagonal elements only. Consists of a diagonal elements. So least squares estimation derivation. Least squares estimation derivation. So outcome is important for us. That is, least square estimated signal is x inverse y. The impulse, the frequency response, what I can say that channel frequency response. Small h I have represented for impulse response. Frequency response of CAR. So I'm considering it as a channel frequency response, or we can say transfer function is into y. Y is the received signal, transmitted signal. Then how you get exact transmitted signal? Because we are transmitting known symbols, I am considering here x. Because I am considering known pilot symbols. So we can compute that. So see here, in matrix form x inverse phi. X inverse because it contains only diagonal elements. Inverse can be computed directly in a simple manner. Inverse can be computed in a simple manner. 1 by x of 0, 1 by x of 1, 1 by x of n minus 1. It comes only if all the diagonal elements are non-zero elements. Remaining matrix elements are zeros. So the estimated channel H cap of L, the frequency, channel frequency response is equal to y of L by x of L. I substitute L is equal to 0 to n minus 1. 0, 1, 2, 3 and so on up to. This is least squares estimation method. Least squares estimation method. H cap of Ls is equal to x inverse y. X inverse y. Minimum mean square error estimation. One step towards the next step one towards ideal, but not ideal, but it is a minimum mean square error. So compute the error, least square error is least square one. This is minimum mean square error. So first you compute the error, compute the mean value, identify the minimum mean value, and give a solution to that, which is MMSE estimation, minimum mean square error estimation. Square error estimation. So by using a adaptive weight vector, we'll get this H cap value. We'll see that error, and with minimizing the error, I will find out the H cap. Minimizing the error, I will compute. That is minimum mean square error. That is only the aim of this work. Minimum mean square error. So this mathematics, some mathematics is there. I will give the direct output. I can say output final estimated channel. Final estimated channel. H cap is equal to RHH sigma z square sigma x square I whole inverse into H cap. Same equation will be implemented in the MATLAB. I will show it to you. This is autocorrelation matrix. This is autocorrelation matrix. Z is the noise, X is the input. This is variance of the noise, variance of the input. I is identity matrix. H is least square estimated channel. Least square estimated. This is RHH is the autocorrelation between H and H cap. So this is the final solution to minimum mean square error. Don't worry about the mathematics. The mathematics is there just for simple calculation, and final answer is this one. So the equations for least square estimation for minimum mean square error is known to you. Just you go to the MATLAB and type all these expressions, you will get these things. I will show it to you. These two equations, how they are implemented in the MATLAB, I will show it to you. Mean square error estimation. These are how the autocorrelation matrix comes into picture, how it is simplified is provided here. So the next one is singular value decomposition method. Into this discussion, I will show you the MATLAB programs DM system. See, this is one program function. This is the function written for least square estimator. This function is written for least square estimator. See what here it is implemented. HLS is equal to inverse of X star Y. That's it. What we have seen, HLS. What we have seen, the HLS. HLS formula is X inverse Y. Is X inverse Y. Same is represented as a function. MS error, that is least square estimator. This is the function HLS inverse of X star Y. Don't worry about this. This is the only thing I want to show you. Estimation. Least square estimation. This is the function. Similarly, minimum mean square error. Same function RYY. It is finally implemented here with all the mathematics. What we have seen here, same will be implemented again in the MATLAB. I will show you that equation implemented in the MATLAB and written as a function. Written as a function XF first computed, then autocorrelation function and inverse of RYY. In RYY only itself is taken sigma y square and sigma z square multiplied with I, identity matrix. You can directly write all these things are not required. You can directly write the program for the MMSE estimator, what we have seen here. It is autocorrelation matrix multiplied by autocorrelation matrix, then this should be done inverse. and variance of noise, variance of X multiplied by identity matrix, and all these things will be here. These things can be shown to you here. Least square error estimator and a minimum mean square error estimate. See, one more example I will provide here. This is another example which you can, sorry, not this example. One more test, yes. So you can see here the simple MATLAB program, what you have seen in the previous, I think previous lab session also you have seen. Random integers. Now in the new MATLAB it is replaced as a rand I. Encoding, convolutionally encoding. The steps what I have shown in the first block diagram will be performed serially in this program. Coding. Interleaving of data. I shown you that. Interleaving nothing but burst errors will be converted into a single bit error. Then binary to decimal. Pilot insertion. Sorry. Then IFFT, cyclic extension. Then channel. This is AWGN channel. You can see the function AWGN, the channel. So it's add additive white Gaussian noise channel. Then receiver part. Extension, FFT, pilot synchronization, demodulation, de-interleaving, all. Receiver signal and bit error rate calculation. Complete implementation wherein is not considered any channel estimation part. So I have shown you this least square estimation, minimum mean square error estimation program. These two can be written as the functions, and already you have written the ofdm program, and you can apply this and you can see the result. See, estimator and the minimum mean square error estimator will be estimate the impulse response at pilot symbols only. Once you estimate the impulse response at pilot symbols place, remaining complete impulse response can be calculated by using either time interpolation mechanism or frequency interpolation mechanism. Interpolation mechanism or frequency interpolation mechanism to estimate the final impulse response. To estimate this is another example where you can see all the parameters will be defined. Locations are considered. Pilot locations and strength. Then FFT matrix. Then generating random channel coefficients. You can see here. Random function used. Data QAM modulation. QAM modulation. That is quadrature amplitude modulation is used here. Program of in IEEE transactions and molecular technology paper, exactly same paper is implemented with the same values. You can refer this paper for better understanding of this complete system. So, channel estimation is at this place. Transmitted pilots. Then whatever equation we have seen, that equation will be improved because is implemented here. With the variables what is there in the previous one, the same variables are implemented here. This is the channel estimation part. Then QAM demodulation. You can see for better understanding. Only thing the variables are given different names, but the program is a very simple one. What I have shown in the first slide was implemented. And you can refer this paper. Same paper is as it is implemented here, MPSK or QAM modulation for probability calculation. So these are the programs to compute the channel estimation. If you are ready with implementation of ofdm, channel estimation part is a very simple one, but a good number of modifications have been done in the literature for channel estimation mechanism. We'll see that now. One of that is singular value decomposition. One of that is a singular value decomposition. In the 1998, one of the person has written in the paper IEEE transactions using singular value decomposition for channel estimation. He modified MMSE channel estimation. That is here. In the channel, we have to compute the impulse response. We have to compute the inverse of the channel. Here, he used singular value decomposition for that matrix to compute characteristics. We'll see that. So first we'll see what is singular value decomposition. A matrix manipulation mechanism where a rank of that matrix will be reduced. So consider a matrix X, U, S, V transpose, where U is M by N matrix, S is N by N diagonal matrix, where it consists of all singular values. I will show you with an example how we can calculate singular value decomposition matrix by our own. I have done that problem. Same I have reproduced here. So V is N by N matrix. So any matrix X of size M by N of real value data can be decomposed into U, S, V transpose. Same is expanded here. X is equal to U1, U2 and so on up to Vn. Sigma 1 to sigma n diagonal matrix. V1 transpose to V transpose. Once you apply singular value decomposition, the first few singular values in general, the first few singular values represent the important components of the signal. The last singular value components, noisy components of the signal. This forms basis for denoising of signals, compression of images, and even channel estimation part. Here we have used that singular value decomposition. As it is a low rank approximation, that's what I have now mentioned. Noise effects, smaller singular values. So we will reduce the smaller singular values to denoise the signal, either our signal or image. So good approximation is how many singular values you should consider. Singular values you should consider. We'll see that. We'll see that with a good example. So to understand how to solve for SVD, let's take the example. A is equal to 3, 1, 1, minus 1, 3, 1. Transpose is computed. I got the answer 11, 1, 11, 1. Eigenvalues are computed. You can see computation. Lambda is equal to 10 to 12. So computed eigenvalues of the matrix A into A transpose. Now eigenvectors for lambda is equal to 10, 1 and minus 1. Eigenvectors corresponds to lambda is equal to 12, 1 and 1. You can substitute the scenarios and you will get the eigenvectors for lambda is equal to 10 and lambda is equal to 12. And 12 and 1 are taken in one columns. This is corresponds to 12. This is corresponds to 10. Normalization of eigenvector. Normalization of eigenvector. It is row column wise normalization will be done generally. The first element is 1. The second element is 1. So 1 by under root of 1 square plus 1 square. Similarly, 1 by under root of 1 square plus 1 square. This is also done in column wise. 1 divided by under root of 1 square plus minus 1 whole square. 1 square plus minus 1 whole square. This is how the eigenvector matrix is computed of A into A transpose. Now do the next A transpose into A. We'll do analysis for into A. A transpose into A. So A transpose into A, matrix is computed. 0 lambda is equal eigenvalues. And for each eigenvalues you have computed, that is not provided here. Directly I have written with, after doing mathematical calculation, I have provided here. Lambda is equal to 12. See, the eigenvalues are arranged in the descending order. So first lambda 12, then lambda 10, then lambda 0, then matrix I got 1, 2, 1, 2 minus 1, 0, 1, 2 minus 5. Column wise normalization. Column wise normalization. Column wise normalization. So 1 by under root of 1 square plus 2 square plus 1 square. 2 by under root of. So column wise normalization is performed. This result. 1 by root 6, 2 by root 5, 1 by root 30, 2 by root 6. These are all values. So now we'll see the final V transpose, and S is eigenvalues. So A is equal to U S V transpose. The eigenvectors of A into A transpose. V is, 1 second please, one call. I'm getting one call, please. Sorry. Shankar Chapanda. నమస్తే చెప్పండి సార్. ఓకే సార్ కదా వస్తా. 11 o'clock వచ్చేస్తా కదా. రైట్ వచ్చి. Sorry. So I will show it to you in the MATLAB with the same example what I have considered. 311 minus 131 USV transpose. So you can see here, you just A is equal to matrix elements considered here. The matrix elements considered 311. 311 minus 131. 311 minus 1 minus 131. Right. Minus 131. So I considered A. I'll perform SVD of A. Directly a function is there in the MATLAB. SVD of A. So I should see the help, because it's returning only some values. To get all values, what I should return? To get all USV transpose. So yeah, it's USV of SVD of X. Then it gives all values. So I will write USV of a same matrix what I have taken the example. See here, this is U. What is U actually here? U is 1 by root 2, 1 by root 2, 1 by root 2, 0.707, 0.707, 0.707. And the negative signed one, and U matrix completed V. S matrix is root of 2, root of 12, and all these values. You can get the simple mathematical manipulation. Mathematical thing, and you can do for a matrix 100 by 100 or 200 by 200. Then you able to get the advantage of your computation. Singular value decomposition. So these are all singular values. These are all singular values. So we'll see that now. Continuation. The command used to compute the singular values on function. So channel estimation using SVD, OED Force, M. Sandel, Van de Beek, Wilson. OFDM channel estimation using by singular value decomposition. The paper written in the 1997. So this is the final thing what we have seen. Estimation. So RHCIR U tilde U Hermitian. USV. Now instead of taking all singular values, I will consider only certain singular values, not all. That's the basis here. Taken here completely. So only some of the singular values will be considered so that the autocorrelation matrix calculation and its inverse calculation will become simplified. So this is SVD for channel estimation method. You can read that paper and the same statements will be provided in that RHH is U tilde U Hermitian. That is only modification in tilde, that is singular value matrix. S matrix is modified. S matrix will be modified. Remaining things will not be modified. That is singular value decomposition. A good matrix representation, but has a good number of applications. Processing, image processing, communications. All these cases, 3 cases, SVD has been utilized for different applications. So, one of the method I have proposed in my PhD, part of my PhD work, I have done EMD based adaptive filtering. So MMSC continuation, the next one is adaptive filtering. All you know, adaptive filtering is initially we will consider an FIR filter with a random impulse response, and you know applications of adaptive filter and how it can be implemented. I will show you the diagram. The diagram is also there. Filtering. Now I have modified this with the empirical mode decomposition based adaptive filtering. I have done channel length estimation and channel estimation. Estimation is done using Akaike information criterion. Channel length estimation is done using Akaike information criterion. Then channel impulse response is estimated using adaptive filter with EMD. I will show you that. See, one thing I have taken here is that adaptive filtering, general adaptive filtering, uses random initial weight vector as a random initial weight vector. But I have modified this with some means. I will show it to you. The novelty of this paper is that decimated version of the one of the decomposed IMF of OFdm symbol as an initial weight vector. Once I get a received OFdm symbol, I will perform empirical mode decomposition. Once that methodology has been performed, we'll get different IMFs. Statistical calculation, I will select one of the IMF as a initial channel impulse response, but I will not directly give that selected IMF as an impulse response, because another in similarly parallelly I'm doing channel length estimation. So from the channel length estimation block, it gives what is the length of the channel. Now the identified or selected IMF, intrinsic mode function, is downsampled or decimated to the length of channel length estimated value. So that selection, that will be used as an initial weight vector. The selection of useful IMF component is done based on correlation and kurtosis method, some calculation I have considered there. So this is the method I have proposed actually here. This is the block diagram, how you can use adaptive filtering as a channel estimation. You can use adaptive filtering as a channel estimation. This block diagram to show how the adaptive filtering is utilized as a channel estimation. This is the convergence analysis of the adaptive filtering. The conventional adaptive filtering and the presented or the proposed EMD based adaptive filtering mechanism. Error is computed, and you can see this algorithm is taking less number of iterations to converge minimum MSE value, minimum mean square error. The methodology, instead of using random the initial impulse response, a good initial guess of impulse response is proposed. A good initial guess of impulse response is proposed. That's make the less number of iterations. That is providing reason for getting less number of iterations. Again, it is compared with the different step variable LMS algorithms, variable steps LMS, conventional LMS. Even variable steps LMS, some computational complexity will be improved. So the proposed EMD based adaptive filtering is almost similar to this red color, which is a variable step size LMS. But I have not compared the computational complexity of these two, but this can be done almost equivalent. But proposed EMD based adaptive filtering is resulted in good in even in bit error rate calculation. Even in bit error rate calculation, consider here bit error rate calculation, MMSE, SVD, conventional adaptive filtering, proposed adaptive filtering resulted in less BER value compared to other cases. So that's what the thing I want to show based on related to channel estimation part. What is related to channel estimation part? I want to introduce one of the parameter is generally peak to average power ratio, PAPR, peak to average power ratio. This is one of the problem presented in OFDM system. In general, we'll consider more number of subcarriers. Either it may be 256, 512, or 1024. So at the receiver, at the transmitter side, or the receiver side, we'll add all these subcarriers, leading to high power, leading to high amplitude, resulting in saturation of power amplifiers used at the receiver side. One of the practical problem representing with OFDM system. PAPR. High PAPR is the problem. PAPR is one definition. Power ratio. So, how to reduce this peak to average power ratio is one of the research topic. Important disadvantage, but good number of approaches are there to reduce the PAPR. But thing is that compromise in bit error rate. Resulting in BER. I should get a low value of BER, but with addition of this PAPR reduction methods, slightly increased performance degradation. But however, still good number of articles or good number of research work is going on. Parallelly, channel estimation and PAPR to get an optimum value of BER is still the research part. What is PAPR? And one of the method I have compared in my one of the conference paper is modified exponential compounding method, which is there. Just compared all the different compounding different PAPR reduction mechanisms. Do that. So my task is reducing PAPR without compromising at BER. That is important. That is one of the research idea now. Good number of compounding, good number of PAPR reduction mechanisms are there. But not at the cost of BER. Not at the cost of BER. So one of the interesting research part. Simple explanation. This I have drawn with MATLAB. By using MATLAB, I have generated this spectrum, all those things. Not required. These are all previously discussed. So only thing is a PAPR definition. That is baseband representation of OFDM signal, X of t, power of OFDM, then PAPR is maximum value divided by average value. Average value nothing but squaring and dividing it by total value, total T. It is the name itself representing that peak maximum value to average power. This is average power ratio. Average power ratio. Peak to average power ratio. Peak to average power ratio. So it is taken because it is a power, we are considering it as a 10 log 10 in dB. Signal after application of IDFT, baseband representation of not received signal, this is a OFDM signal, power of OFDM signal and PAPR. Some compounding mechanisms have been performed with some good mathematics. This is exponential compounding technique. Compression and expansion. Compression at the transmitter side and expansion after that. So compounding technique has been proposed and compared. I shown you that results, the proposed and exponential, the amplitude of the received signal, and how the performance of BER has been reduced can be seen. BER, you can see this is a disadvantage with that. No compounding. I have a BER curve, this one. The proposed one is one shown to you. Exponential, you can see exponential. The BER performance is degraded. That is the thing. Not at the cost of BER value. I should not compromise on the BER value. BER is the ultimate thing. However, PAPR is also important point. You have to reduce that. But obtain optimum value is always a task. Two parallel paths, obtain an optimum value, which is important. Right. So this is exponential and modified exponential compounding technique. This is related to some PAPR mechanism. So that's all for my presentation. Mostly I have concentrated on the channel models. For instance, how the least square estimation method, how the minimum mean square error estimation, and how we are implementing those two equations in the MATLAB. I've shown you some MATLAB implementation of basic OFDM systems. SVD based OFDM channel estimation, where that autocorrelation matrix is applied. Autocorrelation matrix is modified using singular value decomposition. And one of my proposed work, EMD based adaptive filtering, PAPR reduction mechanisms, PAPR reduction methods. So thank you for your attention. If you have any ambiguities or questions, please you can ask. Otherwise, you can post to my mail ID. I will show it to you. Your queries to my mail ID to this one, ari_etta@kakatiya.ac.in. I will give answers or I'll certainly provide solutions to your. And if you have any ambiguities now, you can ask me. Narasimha sir.
Thank you, sir. Thank you for your wonderful session and demonstration in the MATLAB. Now, I request the participants, if you have anything to ask, please, you can go ahead.